Okay, so in this video, we're going to look at doing some trigonometric proofs. And a lot of people really struggle with this. A lot of it's because of we don't really know our trig identities. And also there's some algebra techniques that are involved to making the left side become the right-hand side. And everybody seems to have their own approach to doing these. The way that I do these trigonometric proofs is I try to only manipulate one side until it becomes the other. And I'm going to try to be consistent unless I get stuck here. And I'm going to try to work from the left side and make it become the right-hand side. Now, when we are trying to do these trig proofs, you always have to pay attention to where it is that you're trying to go to. So if I'm looking here at this very first one, my end game here is to try to end up with 1 over cosine. So in terms of how to start this problem, I would try to make all of the functions involved have something dealing with cosine in it. And the first one that comes to mind here that we're going to attack is tangent. Tangent is equal to sine divided by cosine. It's one of our quotient identities. So I'm going to use the quotient identity, and I'm going to rewrite tangent as being sine over cosine. So tangent is sine of x divided by cosine of x. And then I have the rest of my problem here, which would be plus cosine of x divided by 1 plus sine x. And I have to think about, well, what would my next step be in terms of how to make this become the right-hand side? Well, my next approach here would be to look at this and say, all right, well, my right-hand side is only one fraction. So I'm going to say, let's try to go through the process of putting these functions together. And so I'm going to go through the process of getting common denominators. So sine of x divided by cosine x times, I got to multiply by 1 plus sine x over 1 plus sine x. And then my second function here would need to get multiplied, the top and the bottom, by cosine x. So I'd multiply top and bottom by cosine x over cosine x. So I'm going through the process of getting common denominators. Now I'm going to go through and I'm going to multiply it out. And so when I do that here, we're going to have, that'll be sine of x plus sine squared x plus cosine squared x, that's my numerator, all divided by, now I'm not going to distribute out the denominator here, I'm going to leave it factored, so I'm going to say cosine of x times 1 plus sine x. So all I did was combine the fractions. Now we're going to look and say, all right, well, what would my next approach be? And so I'm going to go look for an identity. And in fact, we have an identity here. Sine squared x plus cosine squared x. That is a Pythagorean identity. You'll see over here on the right-hand side that sine squared x plus cosine squared x is equal to 1. And so I'm going to use that identity and rewrite my problem and say, all right, well, this now becomes sine of x plus 1 divided by, nothing else changed, divided by cosine x times 1 plus sine x. And then now we can reduce this problem. Sine of x plus 1, I can cancel that out with 1 plus sine x. And that's going to give me 1 over cosine x. So all I did here was I canceled out those two. And that gives me my right-hand side. All right, so we prove this first one here by going through this process. All right, let's look at another one. All right, so this problem here, I've tried to come up with a plan of attack. All right, well, I have 1 plus tangent squared divided by 1 minus tangent squared. I needed to make it become 1 divided by cosine squared x minus sine squared x. Now, you take a peek at where it is that we want to go. Well, my right-hand side here is in terms of sine and cosines. So a first move here could be to rewrite the problem in terms of sine and cosine. So my problem would become 1 plus, now tangent, remember, is sine divided by cosine. So tangent squared is going to become sine squared x divided by cosine squared x. And I'm going to do that for both of the tangent squares. I'm going to rewrite. So I'm just using the quotient identity here. So 1 minus, get my colors, sine squared x divided by cosine squared x. Now, from here, I'm looking and I say, all right, well, I don't want to have a complex fraction. So I'm going to multiply to get rid of the denominators inside of here, which from here, when I do that, I would choose to multiply everything by cosine squared x. And if I do that in the numerator, I would also have to do that here in the denominator as well. And when I do that, my problem will become cosine squared x plus sine squared x divided by cosine squared x minus sine squared x. Well, I now have the denominator that I want. Now I just have to do something here with the numerator. Well, my numerator, cosine squared plus sine squared x, that's an identity, which equals 1. So that equals 1 divided by the denominator. Leave the denominator alone because that's exactly what I want. Divided by cosine squared x minus sine squared x. There is my right-hand side. So, proof done. All right. So, not a whole lot of manipulation done there. All right, so next problem here. So I have cosecant squared x minus 1 divided by cosecant squared x. And I want to see if I can't somehow make that just become cosine squared. Well, in terms of how to start this problem, we have multiple options here in terms of how to proceed. And one of the first things that I could do, if I wanted to, was I could try to split this fraction up, where I would just split it and rewrite it as cosecant squared x divided by cosecant squared x minus 1 over cosecant squared x. Now, some people might say, well, why would you want to do that? Because wouldn't you want to try to keep it all as one term? And in fact, I very well could. I could have used a Pythagorean identity right out of the gate, but I'm just going to do this problem a little differently. Now, cosecant squared divided by itself makes 1. 1 over cosecant squared. Now, we got to go back and think about where does, what is 1 over cosecant? Well, 1 over cosecant is sine. So, I'm going to replace 1 over cosecant squared with sine squared x. And then now we'll go through and say, all right, well, 1 minus sine squared x, that should be something. And if we go to our identities and we look, it's a Pythagorean identity. I just have to rewrite it. So if I look at sine squared plus cosine squared, that equals 1. If I subtract the sine squared on the right-hand side, I could rewrite this problem as cosine squared x equals 1 minus sine squared. So this entire piece is equal to cosine squared x by Pythagorean identity, which makes my right-hand side. So proof done. All right, next one here. Sine of x minus tangent of x times cosine x minus cotan x. Got to try to make that to be the right-hand side. Well, I don't see any Pythagorean identities that I could use right out of the gate. And so my options here are to either rewrite everything in terms of sine and cosine first and go from there, or try to multiply everything out and then see what happens. I'm going to say, let's just multiply this whole thing, this whole left-hand side out, and let's see what happens and how we'll go from there. Now, there could be a better approach, but that's what my gut tells me to do. So I'm going to start multiplying this out. I have sine of x times cosine x, and then minus sine of x times cotangent x, minus tan x cosine x, plus tangent x times cotan x. And we're looking here and say, well, this just kind of made a big jumbled mess. Let's rewrite everything in terms of sine and cosine, because that's what my right-hand side is in terms of only sines and cosines. So I do that, and I get sine of x times cosine of x minus sine x cotangent of x is the same thing as cosine of x divided by sine of x. And then we go, tangent is sine over cosine. All right, so change that. And I'm going to do that for both. And cotangent's cosine over sine. So I'm just trying to highlight everything that I changed. All right, and now we'll start to see, we could get some things to cancel here when we go through. And we'll see that the sine of x cancels with that sine of x. The cosine of x cancels with that cosine of x. And in fact, when I multiply tangent to cotangent, they cancel each other out. And so I'm going to rewrite my problem here, and it becomes sine of x cosine x minus cosine x minus sine x plus 1. And I try to figure out, well, what would I do next from here? Well, I'm going to try to factor this by grouping, where if I go through and I group my terms, I'm going to put the first two terms in a group because they have a common factor of cosine. And really, there's nothing in common here in my second group except for I could pull a negative out. And if I do that, I could try to make sine of x minus 1. And so we're going to do that. We'll see what happens. I pull out the GCF here, and the first one, that gives me cosine of x times sine of x minus 1. Okay. Pull a negative out. So pull negative 1 out. That will make sine of x minus 1 as well. Well, now from here, we have a common factor in both terms of sine of x minus 1. So I finish the process of factor by grouping. Make sine of x minus 1 times cosine x minus 1, which is my right-hand side. So when we're doing these trig proofs, not only do we practice our identities, but we also practice a lot of algebraic manipulations as well. All right, go to the next one here. All right, so I see two rational functions here adding or subtracting from one another, and I need to make it become a single term that is 4 times tangent x secant x. And we try to figure out how to proceed. And my gut tells me that I want to take two rational functions and put them together into one term. And so that's going to be the way I start this. I'm going to go through the process of getting common denominators. So 1 plus sine x divided by 1 minus sine x, that has to get multiplied by the denominator of the fraction on the right-hand side. So I'm going to multiply it by 1 plus sine x over 1 plus sine x. And the fraction on the right-hand side will have to get multiplied by the denominator of the fraction on the left. So it's going to have to get multiplied by 1 minus sine x over 1 minus sine x. Now, I have to multiply out the numerators. Now, I'm not going to times out the denominators just yet. I'm going to leave that for maybe a step after. If I need it, we kind of have to see how this problem goes. So I multiply out the numerator for the fraction on the left. That's going to give me 1 plus 2 sine x plus sine squared x. And that's going to be all over 1 minus sine x times 1 plus sine x. And then we're going to move our way to the fraction on the right, kind of do the same thing. So I'm going to leave that minus there. This is going to make 1 minus 2 sine x plus sine squared x, all over the same denominator. All right, well, now let's put the two fractions together and then see where we end up. So when I'm doing that, I'm going to end up here in my numerator with, let's see what's left. There's going to be some things that cancel here. So I have 1 minus 1, sine squared minus sine squared. And then we have 2 sine x minus negative 2 sine x. So that's going to leave me with 4 sine of x. Now, looking at my denominator, I know I'm going to have to wind up making a tangent and a secant of x, which both of those functions have cosine in the denominator. So I'm going to go ahead and multiply the two binomials together in the denominator, which makes 1 minus cosine. Not 1 minus cosine. 1 minus sine squared x. All right, so that brings me to here. Now, 1 minus sine squared x, we used that previously in this video. That's a Pythagorean identity for me, where if I take sine squared plus cosine squared x equals 1, and I just subtract the sine squared to the other side, and that gives me 4 minus sine x divided by, or not 4 minus sine x, what am I doing? 4 times sine x divided by cosine squared. All right, so we're pretty close to being right there at the end. All right, the last thing left to remember is that when I'm doing these, and I can break up that cosine squared, and I can break this fraction up as 4 times sine of x over cosine x. I don't know what I did there. Times a 1 over cosine x. I break apart the multiplication of fractions, and then we use our identities to finish. So that would make 4 tangent of x, and 1 over cosine x is secant x. All right, so we proved this and made the left-hand side become the right-hand side. All right, next problem here. All right, so looking at this one, now for this problem, we're going to have to use sum and difference identities. And if you don't know your sum and difference identities, I will get them right over here on the right-hand side of the screen. Okay, so I need to break apart the cosine of x minus y and the cosine of x plus y. And so at first I'm going to use this identity here to break up the cosine of a difference. So cosine of a difference, cosine of x minus y is going to be cosine x, cosine y, plus sine x times sine y. All right, so that was my first identity. And now I need to break up the cosine of a sum. So cosine of u plus v. All right, so I'm going to break that one up. That's going to be cosine x, cosine y, minus sine x, sine y. Okay, well, now we look and we're going to see some things cancel. Sine x, sine y, minus sine x, sine y, they cancel. And it leaves me, this is a real short proof, I have two like terms right here I can put together, and that makes 2 cosine x, cosine y. And that is our right-hand side. All right, so we completed that proof there. And the more of these proofs that you do, the better you will get at them in terms of seeing how to approach and how to start the problem. Now, a lot of these proofs, there are more than one way to do them. And so just because I did it this way in their video doesn't mean that's the only way there is to get the right answer. Okay, now let's look at some multiple angle identities here and how to approach them. So when I'm looking at multiple angles, again, for all proofs, you have to really know where it is you're trying to go. And I'm looking at a right-hand side that has a 3x inside of it and a 1x inside of it. So I need to rewrite the sine of 4x as something that has a 3x and a 1x in it, and the same thing for the sine of the 2x. So I need to try to rewrite both of those, showing 3x and 1x on the insides, and that's kind of simple to do. I can say, all right, well, I could rewrite the first one as 3x plus x on the inside, because 3x plus x makes 4x. And the second one, in terms of 3x and 1x, is, well, 3x minus x will make 2x. So I have the insides with what they need to be. Now, we're going to go use the sign of angle sum and angle differences. And say, all right, well, sine of an angle sum, I look over here on the right-hand side, I'll highlight that for you. When I add two angles together, so sine of u plus v, now I'm going to do sine of the angle here, of 3x plus x. That's going to be sine of 3x times cosine of x plus cosine of 3x times sine of x. And then we're going to do the same thing for the sine of a difference. All right, so the sine of a difference is right up under that one we just used. So sine of 3x minus x here. So I have plus, that'll be sine of 3x times cosine of x minus cosine of 3x sine of x. And I just want to look and say, all right, well, does anything cancel here? And I look, cosine of 3x sine of x, I have a positive 1 there, a negative 1 there. And I look at what's left. I have two terms left to put together, so this proof is done. We're left with 2 sine of 3x's cosine of x. That's my right-hand side. All right, slide over and look at another one. So this time we have sine of 4x. And I want to make that become sine of 2x and cosine of 2x. So I need to do something here with the 4x. Now, we can use the same angle sum identity. However, I could do this a little quicker if I rewrote sine of 4x as sine of 2 times 2x. So I'm going to use the double angle formula here for sine. And so the double angle formula for sine, all right, I'll highlight that one for you. Sine of 2 times an angle is equal to 2 times sine of whatever that angle was, so 2x, times cosine of whatever that angle was, 2x. And that is my right-hand side. So that was a one-step proof right there. All right, next one here. 2 cotangent of 2x. I got to see if I can't make that become cotangent of x minus tangent of x. Well, on the traditional set of trigonometric identities, we don't see cotangent of double angles. And so something that we could do here is we could rewrite cotangent as our quotient of cosine and sine. So I'm going to rewrite this to be 2 times cosine of 2x divided by sine of 2x. So I rewrote cotangent as cosine over sine. Now we have double angle identities for cosine and sine. And a lot of people will look at the list and they'll say, all right, well, let's talk about cosine of a double angle. And you look, there's 3 options to use, and some people are like, I don't know which one I need to pick to use here. And honestly, it doesn't really matter because all 3 of the identities can be transformed into one another by using your Pythagorean identities. And for this example here, I'm just going to pick the first one for cosine of a double angle. Cosine squared minus sine squared. And I'm going to rewrite my problem. So what I have is, if I'm using that identity, I have 2 times cosine squared x minus sine squared x over, well, we go use the double angle formula for sine. And the double angle formula for sine is right here above the double angle formula for cosine, 2 times sine x cosine x. Well, here, right after doing that, I make the 2's cancel. So the 2's cancel out. And then we try to figure out how to proceed. Well, I would split this 2 fractions because I need to have 2 terms. So I'm going to split my fractions, and I'm going to have, it's going to become cosine squared x divided by sine x times cosine x minus sine squared x divided by sine x cosine x. And then we can simplify our problem here. So I can cancel out a cosine in the numerator with a cosine in the denominator, and I can do the same thing with the sines in the fraction on the right-hand side. And that gives me cosine of x divided by sine of x minus sine x over cosine x. And we can use our quotient identities here. Cosine of x divided by sine x makes cotangent x. And sine of x over cosine x makes tangent of x. And we made our right-hand side. All right, let's go do another one. This time, we have cosine of 4x equals 1 minus 8 sine squared cosine squared x. And I got to figure out how to proceed. Well, we are going to use, again, we're going to use the double angle formula here for cosine because I'm looking and we have cosine of 4x. I got to end up with just one axis on the inside. And so we're going to rewrite this as, to start with, cosine of 2 times 2x, just like what we did before. And we try to figure out, well, how am I going to proceed here? Which double angle formula should I use? And I'm just going to say, well, you know what? Let's just go use the first one. And so cosine of 2 times an angle, according to our double angle formula, is going to be cosine squared of that angle minus sine squared of that angle. So we got cosine squared of 2x minus sine squared of 2x. And then we have to proceed here. Well, I need to break apart again the angles on the insides because I just want to see one axis and not two axes. So we're going to use double angle formulas again. And when we do that, remember that we have cosine squared here of 2x. So I got to be very careful when I'm doing my double angle formulas. In fact, cosine of 2x would be cosine squared x minus sine squared x. But I really had cosine of 2x squared, so all of this is being squared because of this right here. And then I need to do the same thing with the sine of 2x. Well, double angle formula for sine is 2 sine x cosine x. However, I have sine squared, so all of this is being squared. Now to proceed from here, I would say let's completely multiply everything out and see where that gets us. So I do that, and I start multiplying it out. And sometimes things get worse before they get better, especially if we don't always take the ideal approach. Or the best first step. But this gives us cosine to the 4th power x minus 2 cosine x sine x plus sine to the 4th x minus 4, actually those should be squares, cosine squared and sine squared, minus 4 sine squared x cosine squared x. You say, wow, this thing has really started to blow out of proportion a little bit here, but we actually got something that we needed. We have this sine squared and cosine squared terms. And so I can put those together, and we have cosine to the 4th x plus sine to the 4th x minus 6 cosine squared sine squared. All right, so at least got a term that I needed. I just need to have 8 of them instead of 6 of them. And then I have to think about, well, how in the world do I proceed from here? Well, an idea to go from here is we're going to pick a term and try to see if we can't manipulate it. Because I don't need to have cosine to the 4th, nor do I need to have sine to the 4th power. And what I'm going to do is I'm going to use a Pythagorean identity here. Now my Pythagorean identities are of power 2s. And so what I'm going to do here is I'm going to say, all right, well, cosine to the 4th power is really cosine squared x being squared. All right, so that is going to be my move here. And I'm going to replace the cosine squared with 1 minus sine squared x. And then I'm going to write the rest of my problem. And then we're going to go through and we're going to multiply out or FOIL out or expand that binomial that's being squared. And when I do that, that makes 1 minus 2 sine squared x plus sine to the 4th x. And then you'll see maybe here how that is going to allow me to proceed. Oops. Now, from here, I kind of have to get my thoughts together for a minute. What I'm going to do is I'm going to work here and say, all right, well, I'm going to try to pull out the common factor. Actually, before I do that, let's put these two terms together here. So they're going to have 1 minus 2 sine squared x plus 2 sine to the 4th x minus 6 sine squared x cosine squared x. And here I'm going to try to pull out a common factor between these two terms right there. So I pull out my common factor, which would be negative 2 sine squared x. And the reason why I'm doing this is because I'm trying to create another term that's sine squared times cosine squared, in case you're wondering what the heck my grand plan is here. So I'm pulling out the 2 sine squared x. It's going to make 1 minus sine squared x. And then I have everything else around it. Well, 1 minus sine squared x is a Pythagorean identity. 1 minus sine squared x is cosine squared x. And so we're getting very close now. So we have 1 minus 2 sine squared x and times cosine squared x. And then the rest of my problem, because I didn't really change anything else. Now we put together our like terms, and we have 1 minus 8 sine squared x cosine squared x. And that is my right-hand side. All right, so there might have been an easier way to get an answer there. And just this was just the way I pictured it as I worked my way through. All right, 2 left on this practice set. All right, this time, all right, we have sine to the 4th x, and I need to reduce its powers all the way down into where it's powers of 1. And so we're going to use power reducing identities in this problem. All right, so I'm going to pull up our power reducing identities here on the right-hand side. Okay, so our power reducing identities are in terms of squared terms. So I'm going to rewrite sine to the 4th power as sine squared x being squared. And I'm going to use my power reducing identity for what's here on the very inside. So I want to reduce sine squared x. Well, sine squared can be rewritten in terms of cosine squared. So sine squared x is going to can be reduced to 1 minus cosine of 2x divided by 2. Now, that whole thing is still being squared. And so I need to square that rational function there on the inside. Now, what I can do is use some algebra manipulation. I can pull out the denominator of 2, but when I do it, I got to square it, so that makes 1/4 times 1 minus cosine of 2x, still being squared, and then FOIL out that second fraction. So not necessarily going to do another identity yet. I'm just going to multiply this thing all the way out. And when I do that, we're going to have 1/4 times, that's going to make 1 minus 2 cosine of 2x plus cosine squared of 2x. All right, so I reduced the power of sine down, and now I'm going through and I'm looking back to where I'm going, and I don't need to have any squared terms. All the exponents of these trig functions have to be 1, so I'm going to have to do a power reducing identity for cosine squared now. All right, so the power reducing identity for cosine squared can be rewritten as 1 plus cosine of the double angle divided by 2. And so I'm going to use that. Oops. So it'll be 1/4 times 1 minus 2 cosine of 2x plus, and now I'm going to put my identity in here, so it'd be 1 plus cosine of, now it was already 2x inside of here, so I have to double that angle, so it becomes cosine of 4x divided by 2. All right, and then how to proceed from here? I go back and I look at my right-hand side, and there is no fraction inside of the problem. Everything inside of here, there is no fraction there. So I need to do something about this denominator 2. So I'm going to pull out a 1/2. And when I pull out a 1/2, that's going to make 1/8 here. And then every single term inside of here has got to get multiplied by 2. So it becomes 2 minus 4 cosine of 2x plus, and then I just have my numerator here, 1 plus cosine of 4x. And then all that's left is to combine our like terms on the inside, and we have 1/8 times 3 minus 4 cosine of 2x plus cosine of 4x. And that's my right-hand side. Okay, last one here. Sine cubed x plus cosine cubed x divided by sine x plus cosine x has got to make 1 minus sine x cosine x. And I try to think about how to proceed. Well, I'm going to have to do something here with this numerator, because I don't see exponents of 3 anywhere on the right-hand side. Now, my power reducing identities are only in terms of sine squared and cosine squared. However, we can use sum of cubes here. Remember that the sum of cubes formula, a to the third plus b to the third, can be factored to a plus b times a squared minus ab plus b squared. So I'm actually going to factor this in terms of the sine cubed and cosine cubed, and that's going to make sine x plus cosine x times sine squared x minus sine x cosine x plus cosine squared x all over my denominator. Now by doing that, the sine x plus cosine x will cancel out. Which means that what I'm left with to work with at this point is sine squared x. And I'm going to rearrange my terms, and you'll see why in just a second, plus cosine squared x minus sine x cosine x. Now, sine squared x plus cosine squared x, that should look familiar here. That is our Pythagorean identity. So, sine squared plus cosine squared x is a Pythagorean identity for me. That makes 1 minus sine x cosine x, which equals our right-hand side.